Okay, so today, well, my name's Chris Kolhoff. I'm the author of the Boost ASIO library, and it's a and for anyone who's been wondering, that's how you pronounce it, ASIO. So you can, I don't want to hear any other pronunciation while I'm here. And if you're wondering where that pronunciation comes from and where the name comes from, it is actually the name of the basically secret police sort of equivalent in Australia. Well, yeah, we like to take the mickey out of things. So now I'm going to start off by saying what this talk's not about. If you're looking for an introduction, the door's back there. No, just kidding. I'm not actually going to be going through here are the basic steps to write a program. What I'm going to be talking about are some of the basic concepts, the fundamental concepts that go into the library, and some of my thinking that went behind the design. And what I'm trying to get across here today are those ideas, so that when you come to design your programs, you can use those ideas to inform your design. One of the key design criteria I had when I started out doing ASIO many years ago was that it shouldn't be a framework. I wanted to avoid frameworks and take what I call a toolkit sort of approach. And the way I define a framework versus a toolkit is a framework is somewhere to hang your hat. It's a skeleton, and you just need to add in your code at the appropriate places. Whereas a toolkit to me is more a collection of functions, classes that you can reuse in whatever way you see fit. And in fact, that's the case with ASIO. There's no one right way. I'm not going to tell you that you must design your program a certain way. I'm going to make some recommendations today, but you're free not to follow them. But hopefully by learning about the fundamental design and concepts that make up ASIO, you will be able to use it in whatever way is appropriate to your particular problem. So I suppose I'd like to start off by giving you some background to what was going through my brain when I came up with the ideas behind ASIO. And we're talking a long time ago when men were men, and 2003. And hang on.
You're good.
At that time, so I'd been doing various network programs, and I'd been using more framework-oriented kinds of libraries. And these things were often based around design patterns, and you may, if you've worked in this space before, use design patterns like reactor, proactor, active object. I'm not going to go and explain what all these are, but these are the things that are going through my head. And there were two other things that happened to come together at the same time. And one was that I was working with a colleague who was really into this stuff, and he was all about making the proactor design pattern, which is a design pattern for developing scalable network applications, about making it work in terms of reactor. So he wanted to allow the proactor design pattern to work on as many platforms as possible. Historically, proactor was aimed only at platforms that had native asynchronous I/O. But for him this was not satisfactory. So he went out and developed his own implementation that used whatever facilities were available for networking on the operating system to implement proactor, so that he could write his programs once and have them compile everywhere. He would tell me about this every lunchtime, so we'd go out for lunch and this is what I'd hear about every day. Around this time was when I first discovered Boost, and the first libraries that I got into were Bind and Function, and for me this was a revelation. Discovering that you could use, I already knew about function objects, but discovering that you could adapt function objects arbitrarily, add and drop arguments, it was a whole new world that opened up to me. And these three ideas, the design patterns, this portable proactor, and bind and function, they came together, and I thought, hey, we don't have to use a framework to do this proactor stuff. We can just go and make everything a callback function object. So rather than having programs inherit from an abstract base class and override, the handle read, handle write functions, they could just go and adapt any function object they wanted to use as a callback for the completion. And so, if I actually worked it out, I could probably figure out the exact date when I had this idea, because it was the evening after we'd had a little users group sort of meeting in Sydney for people who were doing similar sort of work. And so I went home and I just hacked this up, and originally everything was a boost function that would get passed in, and it worked. I mean, initially I was implementing using, if people who know, select as the function to target all the operating systems that I wanted. But from there it sort of grew, and I added backends for the different operating systems to try and optimize performance. And I guess, fast forward a few years into Boost, and the review process was also an important point in focusing the original ideas to try and extract the more generic abstractions while still avoiding the framework approach. Okay, so that's where I'm coming from here, and I guess that's a long way of saying that I'm not going to dictate. If somebody sends me a program and says I want to do it this way, I'm not going to say you're wrong unless there is an obvious problem with the program itself. And actually I'm going to highlight some of the more common problems that people have in the talk today. But first I'd like to start off with the basics of any asynchronous program that uses ASIO. There are four main components that make up any program. Oops. The first one is the I/O service. And the I/O service, if you like, you should think of it as your channel to the operating system. It is your communications between your program and the operating system which is performing the I/O on your behalf. Now, I'm not going to, it would be ridiculous if every single I/O that you want to perform had to be submitted through the I/O service. So over the top, we have these things that I call I/O objects, and they provide the object-oriented sort of layer to submit the I/O requests. So in this case, the example is a TCP socket. And so the things you can do with the TCP socket are initiate a read operation, a write, connect, that sort of thing. And the I/O object will go and take that and via the I/O service submit that operation to the operating system. The next thing, and this is, you're not going to just have one of these, and that's an asynchronous operation. A typical application is going to be made up of many, many of them. And I'm going to talk about these in detail in a moment. And the final component is a call to I/O service run. And that is where you actually give the I/O service the opportunity to go and execute the work for you on your behalf, run the callbacks, and so on. Okay, so what does an asynchronous operation actually consist of? Well, first of all, it has to have an I/O object, because as I said, that's how you submit your requests to the operating system. It then has something that I call the initiating function. And that is the particular class of operation that you want to submit, whether that's read or write or whatever. In this case, I'm giving the example of connect. Then you have the arguments that the I/O object will package up for you and pass to the operating system. So in the case of a connect, it's the endpoint identifying the remote server. In case of a read, it would be some buffers that you want it to fill. And the final thing is the completion handler, and that's the callback function object that you would like to be called when the operation completes. Now, every completion handler in ASIO has a signature, and in the case of connect, it's just a single function that takes a single argument of a boost error code, a system error code. In fact, all of the function objects, almost all of them take as their first argument an error code, which indicates not only whether or not the operation was successful, but also, if it wasn't, the nature of the error. Now, some of the operations take additional arguments to their completion handler. So for a read or write, for example, it's the number of bytes that were transferred. And if you look up the documentation for any particular function, you'll see the signature that you're supposed to provide. Now, what happens when you make this call? Well, the first thing is that your I/O object goes to the I/O service and says, hey, I've got something for you to do. The I/O service then communicates with the operating system and creates the work item within the operating system space. Now, I'm just going to, a little digression here. When I say operating system, I'm using the term as a logical term rather than saying that this is actually happening inside the kernel, because some of these operations are actually emulated in user space for you by ASIO. But from the point of view of your program, you should just think of this logical space as the operating system. And I'll come in a moment tell you why it's important that you should think this way. Okay, so it goes and creates the work, and inside the work item, it's storing the handler, which is the completion handler to be called when the operation finishes. You then, in your program, you make your call to I/O service run. Time passes. Then the operating system says, hey, I/O service, some work is finished, come and get it. And the I/O service goes and dequeues that work item out of the operating system and into user space. And as it does that, it gathers the result of the operation, which, as we saw, is like error code plus bytes transferred or whatever. Then your I/O service makes the call to invoke the completion handler. And so in this case, it just calls the function, passing the error code with the result. So that in a nutshell is what happens when you make a call to run an asynchronous operation. But a real program doesn't just have one operation outstanding. It has many. You'll have many I/O objects and many operations outstanding in the operating system at any one time. So you can sort of think of a program as if it's been running for a while. It's going to look something like this, with many objects sitting in the operating system. And your program will be calling I/O service run, waiting for something to complete. When that happens, the I/O service will dequeue that one completed operation into user space, and as we saw before, we'll call the handler. Now, you might be thinking at this point, well, hang on, what happens if it finishes up and dequeues everything out of the operating system? What then? Well, in most ASIO programs, you will take the opportunity when you dequeue a work item to initiate another asynchronous operation. So in the case of after you've connected your socket, the first thing you might want to do is initiate a read. And that goes back around in a loop back to the I/O service and submits a new piece of work into the operating system. And so your program will continually be regenerating pieces of work, and that keeps your program running. Once all of the complete pieces of work in the operating system finish, then only will your I/O service run finish. Yes?
So if you have these multiple I/O objects, can they all use the same I/O service, or do you have multiple I/O services for each?
So the question is, do you have a separate I/O service per I/O object? And the answer is no. You usually, well, by default, I should say you should just have one I/O service object. In more complicated designs, then you can have more than one if you choose. But generally, yes, you will share the one I/O service between many I/O objects.
Can you call run on the IO service instance more than once?
So the question, can you call run more than once on an IO service? And yes, and that is one way of introducing threading into a design. You'd call it. So, well, it depends what you're asking. If you're talking about having multiple threads call run, that is one way. You can also serially call run. If you run out of operating system work, you can reset the IO service and use it again for another call. When I say I don't want to dictate design, that is one perfectly valid design option for a program, is to have a program that's just a sequential set of calls to run, where you just run a limited number of asynchronous operations at any one time, but then go back to doing something else in your application in the meantime. So yes?
So, excuse me, when you call run, it immediately returns? Or does it pause until all of the work handlers or the work items have been completed?
Okay, so the question is, does run immediately return, or the answer is yes, it waits until all the work items have completed by default, but you can explicitly stop it if you so choose and leave the work items pending in the operating system and come back and call run later to collect them, if you want to do that. So while you do need to call run for the operations to finish, you don't have to call run at any given time while there are outstanding operations. So yes, Dave.
So if you're doing that, I think what I'm understanding is that all of your own code, including callbacks, end up running synchronously, in the sense of there's no concurrency, and unless you explicitly.
So yes, so Dave's saying that the callbacks run synchronously from the point of view of the application, in that you have complete control over when your callbacks are called by making the call to run. And actually, we'll see later that this is key to managing concurrency in your application, because there are times when you don't want callbacks. You want to control when stuff is happening in your code. Okay, so yes, and then we've already covered this. The IO service run just keeps going until all the operations have either been collected from the operating system or it's explicitly stopped. Now, you can just toss all that away now. Well, you should keep that fundamental operation in the back of your head. But in general, when you're writing an application, there's a simpler model that you can use, and that is just to think in terms of asynchronous operations and their completion handlers only. And forget about all this communicating with the operating system and that sort of thing. Because when you think of your application in these terms, you can start modeling it as a chain of operations. And so here I've got a very simple example where it starts off by initiating an asynchronous connect operation on a socket. When that completes, if there was no error, it initiates an asynchronous read. When that completes, an asynchronous write. When that completes, an asynchronous read, and round and so on until an error occurs. Now, if you start modeling your applications this way, well, then you can start drawing your protocol diagrams basically like this. And I've actually got some tools coming up for Boost 147 that actually make it easy to see what is going on inside a running program in much the same way. Okay, so given that, sorry, yes?
So on that, actually, is it not the case that really you could define it in terms of a standard state machine? Or is there something different about what you're...
It's a little bit different, because the states, if you like, are actually the red lines. They're not the handlers. I mean, yes, you can write programs as a state machine, and as you transition into an asynchronous operation, you would put your state machine into that particular state, and when that operation completes, you would compute.
I was just thinking of it from a design perspective.
And that's a perfectly valid way of designing a program. It's not the way I generally choose to use it, though. The way I tend to write programs is more in this sense. It's almost like imperative programming. It's just that things are strung out in a chain rather than happening in a single block of code. Yes, Dave?
So I've recently had the pleasure of doing some asynchronous programming in Python using Twisted. Yeah, I assume you're somewhat familiar with that architecture. It's has a lot in common. One of the things that I found rather painful was that sometimes, the ethos is you do everything asynchronously. Don't make your program block for anything.
Mm-hmm.
But I found that sometimes there's a sequence of things that you want to do, or something that you could write easily as an imperative function with control structures, with a bunch of places where it has to do these asynchronous things, and breaking it all up into separate callback functions is tedious at best.
Yes,
and
yes.
error-prone.
Okay, so Dave's comment, yes, is that the spaghetti code you end up with can be a bit tedious and error prone.
Do you have a strategy for
I do, and if you'll come to my awesomeness talk, you'll get to see it.
your awesomeness talk? I will come.
No, I mean, it's not actually just about what you can do in C++ OX. I'm actually a reasonable proponent of using coroutines to manage this sort of stuff, but I tend to prefer, and I will talk about this in my other talk, stackless rather than stackful coroutines, for people who are familiar with the term, just because in massively scalable programs it gives you much more control of the memory usage and so on. Okay, so, all right, given that, what are the key challenges that I see if you're designing asynchronous programs using ASIO? Well, the first one, and most fundamental, I think, is managing your object lifetimes, because you're not dealing with a synchronous sequence of calls where you're just using objects that are on the stack. You now have to deal with the fact that you will be exiting scopes while objects are still in use. The next thing is how to think asynchronously when you're designing your programs, and particularly the common pitfalls you might fall into if you haven't quite got the right mindset. Then I'm going to talk about how I see best to use threads in conjunction with ASIO, and finally how to manage complexity in a growing program. Okay, so object lifetimes. So if we just take a set of common asynchronous operations, we've got our I/O objects, we've got our arguments, we've got our completion handler. Now, what are the rules that ASIO guarantees for your program when it comes to these participants in asynchronous operations? Okay, well, the first thing is that where ASIO declares the function to take the argument by value, ASIO says, I will take a copy of that argument for you, and you can just let that one die, I don't care. And I will keep that copy for you until the asynchronous operation completes. Makes a similar guarantee for the case when the arguments are passed by const reference. And usually the distinction between the two is I usually take the handlers by value simply because I want to document the fact that it can call the non-const function call operator, if you like. In 1.47, if you're using C++ OX, I've actually started taking handlers by R-value reference, but same guarantee will apply. That in that case, it's going to make a copy of the object and maintain it for the lifetime of the operation.
But it's not going to make a copy of the buffer when it's.
Okay, this is not a no. Okay, that's true, right? In the case of buffers, buffer objects in ASIO are shallow. They don't own the memory associated with them. So it makes a copy of the buffer object. It is your responsibility in the application to guarantee that the lifetime is maintained until the operation finishes.
So you're just pushing the problem one level.
Yes, that's right. Because the buffer objects are actually templated arguments, though, you can, if you want, roll your own buffer objects that do reference counting, or in some other way do the lifetime management for you. But the ones that ASIO provides by default do not do that.
So why wouldn't you just pass by value in C++OX?
I might leave the answer to that for. Well, the question is, why wouldn't I just use by value and by R value reference? Yeah, I'll come to that in the other talk.
Okay.
I don't want to give away too many spoilers, otherwise I have nothing to talk about.
I didn't realize that was all other topics.
Yeah. Actually, most of what I'm copying in this talk is all valid C++ 03. I'm not really going to talk about anything C++ OX specific in here, because I don't know about you, but in practice, everything I'm doing is still, I think it's GCC 4.1, so I've got no alternative.
So one last question. From the point of view of the client of your library, are const reference arguments and value arguments the same?
Yes, that's right. And I think the standard says similar things for many things. It says that the implementer of the library can choose, I can't remember, I think I read that somewhere. But
and I don't remember the status.
So, yes.
Please repeat the question.
The question was,
Sorry.
from the point of view of clients of this library, are const reference arguments and value arguments the same?
Yeah, so are const reference and by value arguments treated the same for the purposes of using the library? And the answer is yes. Okay, then we have arguments that are taken by non-const reference. So they're output arguments for the asynchronous operation, and they, in this case, you as the user have to guarantee that they remain valid for the lifetime of the operation. And finally, we have the I/O object. In this case, is when the I/O object is passed as the this pointer for the operation. Now, okay, as a general rule, I would say you and your application should guarantee the object remains valid for the lifetime. But in certain cases, ASIO will say, well, if the object is destroyed while doing the operation, it will just cancel the operation for you. But in general, you shouldn't rely on that in your applications unless you are only using the lowest level operations within ASIO. I'll come to that later when I start talking about how to manage complexity. Okay, so question for the audience here: what's wrong with this code? Does anyone want to make a? Yeah.
Buffer is going, also the actual buffer data is going out of scope.
Okay, so the answer yes, that's right. The buffer data, which is the message object, is going out of scope. And this seems to be a common newbie error. Now, we did cover this already. It is the application's responsibility to guarantee the buffer remains valid. If you do make this error and you're using a compiler which has iterated debugging, I think recent Visual Studios and GCCs, you'll get an assertion because ASIO will capture an iterator into the string object for you and then test it at the end of the operation to see that it's still valid. Okay, so what?
That's a runtime?
Yes.
Yes.
Yeah. Sorry, yes.
Was the problem that the buffer is going out of scope before IO service run is called?
Okay, so the question is the problem that the buffer is going out of scope before IO service run is called? No, it's more than that. It's that it's going out of scope. When you initiate an asynchronous operation using async write, it's completely asynchronous. There's no guarantee when the actual I/O will occur. It may occur within the call to async write. It may not occur until you call IO service run. It may occur at any point in between.
So I think what he said is correct on that basis. If what you're saying is that it's guaranteed to complete by the time the next IO service runs.
No, it's not. No,
Could
sorry.
be done from a handler.
Yeah, run would mean another thread.
The IO service already running.
Oh.
But
No, it's not that the call to IO service run occurs. It's that the actual completion handler for the operation goes. Because just because you called IO service run doesn't mean the actual operation has completed. You may call IO service run and then explicitly interrupt it for whatever reason, and the operation is still pending. You still have to guarantee the buffer at that point.
Okay.
Right? Because these operations occur. Okay, this is why I drew the operating system as a cloud. you should think of the operating system as a context where stuff occurs asynchronously to your program. So once you submit something into the operating system, you don't really know when the operation itself is going to occur, and you should not try to rely on any knowledge about ASIO internals about when it actually does occur.
Nor the order, if you have multiple items.
That's right. You should not
No way of
what,
determining.
make any assumptions about the order in which things occur.
So is it true that even if you're not saying explicitly, return right away when you call run, that it might not complete all of the I/O that's currently pending before it returns?
Sorry, I got a bit confused in the question.
Will I/O service run always complete all of the pending I/O?
Okay, will I/O service run always complete the pending I/O? Yes, if you don't explicitly stop it. Or, sorry, there's two ways in which you can stop otherwise. One is you explicitly stop. One is that an exception escapes from a handler. In both cases, you can then go and restart the run if you need to keep going.
Cool.
Yep.
So basically, the only time that we can release the buffer is when our handler is called.
The only time we can release the buffer is when the handler is called. In general, yes. In practice, if you use custom buffer objects, because I said the buffer objects are template parameters, ASIO actually makes a slightly different guarantee that it will keep a copy of your buffer object until it no longer needs it. So if you reference count your buffer object somehow, then that is enough. It will go out, like the memory will be released automatically at that point. If you're using the shallow buffer objects that ASIO provides, then you should keep it around until the handler is called. Yep. Yep.
Is it the case that that multiple operations can be called in any order, even if you're using a strand?
Okay. Maybe we'll come back. Sorry, the question is relating to strands. I'm going to talk about threads later, so we'll come back to that. Okay, so how should we deal with managing lifetime of the objects? So let's just go back to our example of this simple use case where we've got a connect followed by a loop of operations doing read and write. The first strategy you can use is just to make sure that your object outlives any call to IO service run. And in very simple programs, this is probably a good approach to use. And actually in some complex ones too, we'll see at the end. So really all this is saying, because I guarantee that I'm only going to be calling your completion handlers inside IO service run, provided you don't call run afterwards, everything's sweet. Okay? But in general, you're not going to have an application which just has one connection object. You're going to have an application which has 100 or 1,000 or 10,000. Okay, so before I get on to the next strategy, is another question for the audience. When does object lifetime begin and end? According to the standard.
Begins when the constructor ends and ends when the destructor begins.
That's right. So the answer is begins when the constructor ends and ends when the destructor begins. So what's wrong with this code? Anyone want to make a guess?
The socket's gone by the time you're constructing the connection.
It's not so much the socket's gone. The socket object as a member is still valid. The problem is that you may have left it till the destructor with some asynchronous operations still pending. And so you have things that may still be accessing your connection object by the time you arrive at the destructor. So if we say that we're in a case where we're running these connection objects, okay, in practice you're not going to experience that usually as a problem, because people all the time they spawn threads inside constructors, but as a general rule, if you see this in ASIO code where you are trying to cancel your asynchronous operations by closing a socket in a destructor, you're too late. By the time you reach the destructor, your objects that you've bound into your completion handlers and so on are no longer alive according to the standard.
I think what's missing for me in understanding this is what role connection is actually playing.
Okay, so
You haven't said how that
Sorry.
fits into the rest of the system.
each of these here are they're member functions, say, of the connection object. So that each piece of code in the box is inside a member function that's been bound up using BoostBind to use as a completion handler.
Okay.
Okay, so if you still have these outstanding handlers associated with outstanding operations by the time, whoops, which way am I going here? By the time you reach the destructor, you probably have something wrong in your program. Okay, so this is a warning sign. So how should you deal with this? Now, the strategy I recommend using by default will derive from first principles, if you like. So the first thing is to note we have a chain of operations here, and the chain continues for as long as the connection object has something to do. So first thing to remember is that we want to keep the connection object alive for as long as the chain of operations continues. The next thing is to go back to my original explanation of how asynchronous operations work, is that for each asynchronous operation, the operating system is storing a copy of the handler for us. And it will store that copy of the handler for us until the operation completes. And the final piece of the puzzle is that I said that ASIO will take these by-value arguments and store them for you. So we put that all together, and the default strategy that I recommend is to use shared pointer and enable shared from this. So what you do is inside every asynchronous operation, when you start it, into your completion handler function object, you bind a shared from this. And so that, has anybody not used enable shared from this before? Okay. Doesn't matter. I'll explain it. I've got confirmation I need to explain enable shared from this.
Can you help with that explanation?
I might do. Okay, so shared pointer, as I hope most of us know, is a reference counted pointer. And sometimes you will be in a circumstance where you need to convert from the raw this pointer of an object into a shared pointer. Now the default thing you might try, which is to construct a new shared pointer from the naked this pointer, does the wrong thing, which is it will create a new reference counting context, and you'll now have two reference counting contexts going against the same object, which is bad things are going to happen. So what you need is a way to be able to obtain a valid shared pointer for the original reference counting context associated with it. And so enable shared from this does that for you. It's you inherit from it, and it gives you a function. It's a member function of enable shared from this called shared from this, which returns you a valid shared pointer for that object. So provided
you start with having a shared pointer pointing to connection object.
That's right. So when you first create your connection object, you should pop it into a shared pointer somehow, and then from then on, whenever you want to use it in some lifetime extending way, like putting it into an asynchronous operation, you should always use the shared pointer rather than the naked pointer, because if you don't, then it might disappear while the operation is still pending. Is that clear enough?
So these handlers that you are using are actually more like function objects or closures, because they have data with them.
Yes, they are function objects. In fact, it'd be a very rare case when you would actually use a standalone free C-style function as a completion handler. You will almost always be using something like BoostBind or rolling your own function object or Lambda in C++ OX or something. Okay, so then the next question becomes, how should you correctly, if you want to get rid of your connection object, what do you need to do? So let's say in this case you're going through and, I don't know, expiring all dead connection objects, or you want to disconnect anybody you've used a thread, or I don't know. How do you explicitly close that? And so what you should do in your object is you should create a function, I'm calling it stop, that in this case closes the socket. And what closing the socket does is it cancels all outstanding operations. Now they may not finish straight away, but it asks the operating system to terminate them, and then at some point in the near future they will all complete, and your object will now have the opportunity to clean up.
Is there some subtle reason why you named it stop as opposed to close?
No, you can name it whatever you like. Except that in my case I like to call the counterpart on the construction side start. Because the way I like to think of it is that you're starting off a chain of asynchronous operations, and then at the other end you are stopping the chain of asynchronous operations.
And that's because of the thinking of all the completion handlers additionally calling more function objects that create that chain. So you're starting something as opposed to just simply having a connection that does nothing on its own.
Yes, so you're saying basically yes, because you're thinking of it in terms of chains of operations that...
Okay.
Yes.
So when does close...
Sorry, I thought I was paraphrasing the question. Sorry. Was that a fair summary of your question? Yeah. Okay, so
when does socket close return? When all the jobs are cancelled, or
no? When does socket close return? It returns immediately. It is like a one-way message passing communication.
So when you can actually delete the connection.
When do you know when to delete? That's what the shared pointer is for, because all your operations will complete, and at some point afterwards.
Oh.
Okay, and because the shared pointers are keeping your object alive, that is the opportunity for them all to disappear.
That assumes that the connection object is always on the heap.
It assumes the connection object is always on the heap. Yes, and in general, in a complicated program, it probably will be. Like if it's a single client where you only have one connection, then you can probably take the approach which I had earlier, where you just put it on the stack. But most of the programming I do is all server-side, and we're talking hundreds or thousands of connections. So, now, once you've got this, now that we have in the standard, I think recent versions of Boost, we have make shared to create a shared pointer. I like this as a nice little way to kick something off for a connection. It's just to use make shared to create the connection object, and then in a single line start it. Now you don't need to collect the return value of make shared, because what you're actually doing in the start call is you're sort of pulling the lifetime ownership of the object down into the operation which you're kicking off at that point. Okay, so the next set of challenges I think go through how to think asynchronously in your designs. So I'm going to go back to this problem that I put up before. What is wrong with this code? And we've sort of touched on this already. The second part is that the socket close call returns immediately. It's just a request to the operating system to close the socket and cancel the operations. So even if this worked in the other case, which it doesn't, you're going to exit from your destructor before the operations complete. In fact, if you were doing this from inside the IO service run call, it is guaranteed that is going to be the case, because the next completion handler can't be called until you return control back into IO service run. So what should you... Oh, sorry. Yeah, slight digression. This is sort of based on some real production code that I've seen. What's wrong with this code?
Doesn't use date time.
doesn't use date time. Okay. I'm not going to pay that one, Jeff.
Or chrono, yeah.
X times 0.
Well, there's obviously no error checking, right? So
Well, there's two different,
it's not initialized.
there's two different time calls.
Yeah,
Time
Dave's,
0
Dave's
and
correct. It's making 2 calls to obtain the time. Okay, and it was a merge error that this happened. And I'm sure we've seen those sort of things before. It's supposed to be populating the structure with the time in seconds and the time in microseconds, but it's obtaining those time values through 2 different calls. And so the bug that we'd see would mysteriously, time would jump forwards to 1.9999 or and then backwards again. And that's because it was reading the time at 2 different times. So this is why I say you should think of the think of the operating system cloud as this asynchronous blob where stuff happens asynchronously to your program. So in this case, time keeps moving forward. I mean, I know that sounds a bit stupid to say it, but you can't make an assumption that when you make 2 consecutive calls to obtain the system time that you're going to get the same value, because chances are the computer's system clock will have moved forward in the meantime.
Almost guaranteed.
Almost guaranteed, but not entirely guaranteed, because the clocks are usually updated on an interrupt, and so it's possible that if your code executes fast enough, you'll get the same value. So in a similar vein, what's wrong with this code?
Socket could be disconnected.
Yeah, so that's right. The answer is socket could be disconnected in the meantime. It's a race condition. In fact, it's the same principle as the previous example of the time. The state of the socket is stored in the operating system, and it can change state asynchronously to your program, so that even though your program is single-threaded, you're like, single-threaded, I'm not going to have any race conditions. That is not true. You're dealing with objects outside of your program that will change state asynchronously to your program. So the key, I guess, to thinking asynchronously is to start assuming that almost everything around you can change state when it's not under your control. And so conversely though, if you're going to design programs that actually work, you need to identify the parts of your program that are under your control and that will only change state when you make them change state, and so that you know that they're not going to sort of switch values in between things. So in the case of our connection object, the thing that is under our control is whether or not the socket is open. Now this is different to whether or not the socket is connected or whether it's disconnected by the remote peer or whatever. The socket being open is a state within your program, which is the file descriptor or socket handle or whatever, that you have not yet closed. And when you call stop, that's the only time when you are changing state from open to closed. So what I recommend then is when you are writing your programs to shut down cleanly, you have to deal with the fact that you had your outstanding asynchronous write operation or read or whatever. You called stop on your object to in turn close the socket and try and shut everything down. But what happened was that the operating system had already finished your write successfully. So the state of your write operation changed asynchronously to your program from being unfinished to finished. So you can't rely actually on I know I've left it off in this slide, the error code indicating that the operation was cancelled by closing the socket, because it may not have been cancelled due to this race condition. The state that you do have control of though is the socket open or closed. So you should actually check if you are going to allow your objects to be explicitly stopped in this way, you should check some internal state of the object in each completion handler to determine whether or not it was in fact stopped. So the final piece that I recommend if you're going to design your programs in this way using enable shared from this is that you also provide this is stopped as a helper function. And so when you, like this is the general pattern that I sort of recommend that you follow by default. That you derive your objects from enable shared from this and provide the three functions start, stop, and is stopped. Okay, so we're doing on time. The next section I want to just talk about briefly is how to manage threads. And I like to think of it as there's a spectrum of different approaches you can take. And so I'd start from the top, the ones that I'd recommend you use most. And as we move down, you should be using them more rarely, but they're still there if you need to use them. Okay, so the first one, obviously, and this in the same way as the standard, I think, recommends using standard vector as the default container of choice, I'm going to recommend that unless you have some good reason otherwise, single-threaded should be the default threading model of choice. Because once you introduce threads, then you have to start worrying about synchronization and that sort of thing. But there's not much more to say on that, so what I'm going to talk about next actually is how to use threads for long-running tasks within ASIO so that you can execute the task without holding up the main thread of control of your application. And then I'm going to move on to a couple of approaches which probably better utilize multiple cores, multiple CPUs if that's appropriate for your application. Okay, so yeah, as I said, single-threaded, default starting point, but the key though is you need to keep your completion handlers short and you don't block the work in them for any particular length of time, because if you block the work, then no other completion handlers are going to be able to run. But let's say you do have some work that will execute for a particular length of time, so I don't know, communicating with a database or something. How should you integrate that? Well, what I recommend is that you keep most of your logic in the main thread. So primarily your application is still single-threaded, but you have a background thread to perform the long-running work, and when the work completes, the result is passed back for execution on the main single thread to continue the processing. So how does that need to work? So if we go back to our basics, you've got the operating system context with the outstanding work. In this case, we have some long-running asynchronous operation, pseudo-asynchronous operation that we want to run in our own application. So the first thing is to start a thread or use an existing thread and put the work item into the context of that thread. And then the thread goes off and performs the database operation or whatever. And in the meantime, your application is calling IO service run to collect results of operations.
On the main thread.
On the main thread, yes. At some point when the operation completes, the thread posts the result and the handler that's associated with the operation into the operating system context. And immediately the operating system notifies the IO service, which dequeues the handler and the result back into user space where it can call the handler to run the completion handler. So it's very similar to what the operating system is doing for you for I/O operations. It's just that you are performing the operation in a background thread yourself and then posting the result back through the IO service.
So is there a mechanism by which in the completion handler I can tell the run process, which is executing the queue, right, which is looking at all the work objects in the operating system, not to stop?
Okay, well,
there's only one. Oh, okay, go on.
Your question is exactly what I'm about to talk about on this slide. Yes, so sorry, the question is how do you make sure the IO service run doesn't stop while you're doing this work on the thread? And there was a good reason why in each of these little work items I had this work written there, because in ASIO terms, work is an object of this type. And what this object does is it tells the IO service, you've still got something pending. You've still got some work that hasn't yet finished. And when this work object is destroyed, then the IO service can check, has it run out of work, or does it still have more things to do and keep going, and so on. All right, now in the operations that are implemented in the operating system, there isn't a real object of type IO service work. It's just logically you can think of it that there is one. But in your own programs, if you want to provide the same behavior, then you should use one of these. So if you wanted to implement this long-running operation in the background thread in the connection object we had, then so the first thing is you need something to kick off the request to the background thread to do the work. And in this case, so I'm using a hypothetical function async, which is not hypothetical, I think, if you're using C++ or X, to execute something in a different thread. And we're creating a function object here. We're passing in a bunch of arguments which represent the work to be done, but we're also binding in one of these objects of type IO service work to keep the IO service thinking that there's still a pending operation. Then, some point later in the background thread, the do work function executes, and this is where you do whatever it is. And when it finishes, then you call IO service post to post the result back into the main, back to the IO service so that it can run in the main thread.
And when that argument work goes out of scope, that's how the IO service knows that its last bit of work is done.
That's right. And in fact, the post call creates, if we go back here, when you post, you're actually creating another bit of work within the operation. So that still keeps it alive. So the chain of work continues.
Isn't that always the way?
So
Yes.
This is the same as you're essentially creating an event loop, right?
Yes.
So if you can, the only thing that's different from what I think of as a traditional event loop then is to deterministically order the events in your event list.
Okay, so sorry, yes, the question is basically like an event loop, and yes, that's what ASIO is internally, but we're saying that the main difference, well, this is what I would call is the imperative style rather than, well, it's also proactor versus reactor for people who knows those terms. So reactor tends to mean more, it's event driven. When stuff occurs, you will take appropriate action, whereas proactor, the asynchronous model, is you initiate the operation, and when it's done, then you, in the chain, take the next action. But internally, yes, it's all managed as an event loop. Okay, and then, yes, so the final piece is just, it's no different really to any of the completion handlers for asynchronous operations. Is your function that gets called when the operation's finished. Now, just sort of, if you don't have access to some sort of async function already to run stuff on a background thread, you can, in fact, use a second IO service object in your application to do the same thing. So you just need to run an IO service in a background thread, and you can post a completion handler into the background IO service. It will run it, and then when the long-running task finishes, it posts another handler back into the main thread. Okay, so the next approach you might want to use is to use multiple IO services, but one thread each. And in this case, you would tend to use this if you have a design where it can be partitioned cleanly. Like there's a lot of objects that don't necessarily need to communicate, they don't have any shared state or not much shared state. And so you can load balance them across a pool of I/O services. There is an HTTP server example in ASIO that does this. You still need to keep your handlers short and non-blocking as in the single-threaded case, because if you don't, you'll be holding up other handlers running on the same I/O service. And in general, I say you should ensure your objects, because you don't necessarily know the home I/O service of any particular object, and you don't know if it's going to be running in the same thread as you or in a different thread as you should use a message passing approach if you need to communicate between objects. And to do that sort of message passing, the design I recommend is that you make your actual implementation functions private. In this case, I've got do foobar as an example, and your public functions simply post a function object into the home I/O service, and that ensures that the object, so the function runs in the correct thread context of that particular object. Now, I/O service post is perhaps less efficient if you're making calls between objects that actually do reside on the same thread. So you can also use I/O service dispatch, which will, it's like a fast path. If the object is running, if you call I/O service dispatch from within an I/O service run for the same I/O service object, then it just calls the function object directly. It doesn't need to do any enqueuing through the operating system. Sorry, yes, we've got a question.
The dispatch was doing two things. Was it doing what the previous call did if post? Does it do a post if it's not within?
So yeah, yes, the question is, does dispatch do a post if you're not in the correct thread context? Then yes, it does.
So you can always just use dispatch?
You could always just use dispatch if you want, yes. Sometimes though, you may want to guarantee that the function object will not be called recursively. And so in that case, you will want to use post, because that guarantees it'll just be enqueued for later rather than execute immediately. So it's up to the use case which is more appropriate.
So I actually have a use. Oh,
sorry. Go on.
I actually have a use case. I have multiple pieces. I want to just initialize all of the pieces to start loading. At some time, asynchronous. And then I just want to let them run, and then my program is going to continue on, the user's going to interact. And all of a sudden the user says, I want to use that object. It's still loading. And I want to say now, wait till that object completes loading. So you gave that example where you had I/O service run in a long-running thread. How do I tell I/O service run not to stop if there's no work handler? And how do I tell a connection to complete without, what I really want to do is at this point in time where I absolutely have to have the contents, to say, okay, you're synchronous now, essentially.
Okay, so the question is how, there's two parts, I guess. First is, how do you tell the I/O service that it needs to wait, even though it may not have any. Yep. And the second is that, so you've got this long running loading process, you've got objects waiting on the loading, and you want them to start doing stuff when the loading completes. Okay, so the answer to the first part, I had in this example here, you can just use a, I missed it. You can just use a work object. So in this case, I'm using one to keep the background thread ISOs alive, right?
Oh, I see. Okay.
Right, so you can just use a work object that will just keep it running as long as necessary. You can explicitly destroy your work object if you need to shut it down at any point. Okay, but okay, you could, in relation to your loading part, you could use two-step. If you want to do things synchronously, then you could run your iService once to do all your loading, but not kick off any of the other objects' operations. And then when your iService exits because it's run out of work, you kick everything else off, and then just run the IO service again for everybody else.
It's not that simple. I have, say, 150 objects that I'm loading, and I'm just using one of them. I mean, just one of them has to be finished at this time, because that's the one I'm now using, and the rest of them needs to just continue loading asynchronously.
What I would actually recommend, though, in most programs is that you use, or abuse, if you like, a timer, deadline timer class in ASIO, because what you can do is you can set a timer with an infinite expiry, because the date time classes have positive infinity as an expiry time. And so you actually set a timer with a positive infinity, and anybody that's waiting for this object to finish loading just goes and waits on the timer. And so they're performing an asynchronous wait against a timer that notionally will never expire, but when the loading does actually finish, it just changes the timer to expire at negative infinity instead, and suddenly everything that's waiting is released. And anything that doesn't, due to their own loading taking longer, doesn't actually start waiting on the timer until after object A has finished loading, their wait will complete immediately, because the timer is now set to negative infinity. I mean, if you like later, I can illustrate with an example, but
The blank look on my face.
But yes, there are ways to do it, and you don't need to treat things synchronously. I would generally prefer to keep, I mean, you're saying you've got other operations running which are asynchronous still in conjunction with this, so you don't really want to divide half your program into synchronous and asynchronous. You'd like to trigger off certain events, have other events start. Like when the loading finishes, that is an event, right?
Offline.
Yep. Okay, so
Sorry, Chris, one more question here. So you propose the use of the deadline timer as a lock on a service.
It's more, okay, praising deadline timer as a lock, it's actually more like an asynchronous condition variable.
Condition variable, right? So so as soon as you talk about condition variables, then you start thinking about, okay, there are a whole bunch of locking primitives that you normally use to when you're doing threading. So this is new to me, so I'm asking you, do you have this documented somewhere as to the kinds of locks that you can perform?
Well, all of this works just perfectly fine in a single-threaded program, so it's not locking as such. Some of the examples do illustrate this usage. So, because I prefer not to dictate designs, the use of deadline timer is only one way to do it. You can also do it by storing objects, like the next piece of work in boost function objects or whatever. It's just one particular way I like to use. Sorry, yes, multiple IO services. It's fairly similar to the using, one IO service, multiple threads. Yes, fairly similar to multiple IO services, except that this time you need to deal with the fact that your handlers can be called from any thread that you call IO service run. So you now have the issue of some of the logic in your class may execute concurrently. So for that, ASIO provides an object called a strand, which I'm going to cover in a moment. But similarly to the previous design approach, all objects really should communicate by message passing anyway, but this time it's because of the strands. Okay, so a strand, at a high level, you should just think of it, it just means that a set of handlers that don't execute concurrently. And a strand can be implicit. So if you just run one IO service from one thread, so your entire program is single-threaded, then I call that an implicit strand, because it's implied that your handlers will not execute concurrently. Another example of an implicit strand is when you just have a single chain of asynchronous operations. You never have more than one outstanding asynchronous operation at a time, and so once again you cannot have the logic execute concurrently. But of course, in any complex application, you're going to be running multiple asynchronous operations simultaneously, and so you do need to deal with the fact that your completion handlers could run on any thread. And so that, sorry, this is the example of you could have each one of these as a single chain, but because they're all separate objects, the separate objects can execute on different threads, so the load will be spread across multiple CPUs, but any given object, only one handler can run at a time. Now,
Sorry, there's something in the way that you're talking about this that there's a gap for me. You talk about objects as though they have a particular relationship to I/O services, I think. In other words, you made this framework where you do everything in terms of functions, great, and then you say, but often you're going to do this binding, and then whenever you talk about, you're going to bind objects into these function things that are are just like boost function, and then when you talk about objects, it sounds like there's some assumption that each one is only associated with one I/O service?
Okay, so just trying to paraphrase, am I making an assumption that each object is only associated with one I/O service? In this design approach that I'm presenting in this talk, where you use enable, shared from this and so on, then yes, I say generally you would be, because so in the case of the connection object, your connection has a socket. It might have two sockets, which we'll see in a moment. It might have some timers and whatever. I would recommend that all of the I/O objects associated with that connection do run on the same I/O service. Yes.
Part of my conceptual problem is that I don't even know what do you mean by a connection? I mean, what are you trying to group together in that object?
What is meant by a connection, in this case, protocol logic. It is all of the logic, all of the buffers, all of the state necessary to manage that particular connection or whatever it is. So if it's a mail server, it's going to include your user ID, the home folders. So it's all of the state necessary to manage that particular remote connection that you've accepted from somebody. Does that help?
I think so.
Although ASIO only provides the low-level I/O building blocks for doing X, Y, Z, in a real application you're going to have things to parse messages. You're going to have a message format. You're going to have all these things. They all have their own state that needs to be kept in the application. ASIO won't do that bit for you. Right. And so, yes, as a general design rule, you should group those together in this design approach into a single object where anything within it uses the same I/O service, so you can manage the concurrency and only manipulate that state from one thread at a time. Okay, so yep.
Okay, since you have this picture on the screen, so this would be like a synchronous way of thinking. You do this, and then you go into a loop, and right?
Yep.
And then when you go to asynchronous, you get the inversion of control, because you write these handlers, and you suddenly deal with multiple handlers. Are you also undoing the inversion of control?
Am I undoing the inversion of control? Yes, in a way. I mean, in this code, it's still inverted in the sense of your execution returns from the function, and you have to wait for the event for execution to continue in another function. But in the way you think about and design your application, I recommend thinking about it as you being in control of the event. So you do a read, and then you do a write, and then you do a read, rather than the completely inverted model, which is socket says I can do a read now, or socket says I can do a write now, and taking action in response to that event.
So you are undoing inversion of control in your head?
Yes.
So how is this different then from the full inversion of
How is this different? Well, hopefully, because we are running short on time, in the last section, we'll talk about how you can use this to create larger abstractions within your program. which one of the key problems I had with the reactor pattern is that it was very difficult to create higher level abstractions on top in a way that they could be easily reused. So yeah, we'll come to that in a moment. So just in terms of strands, we had this previous example, very simple, only a single chain of operations, but let's say that our connection was actually a proxy, so it's communicating between two connections, a socket downstream and a socket upstream. Then in this case, it's going to be after the initial step of establishing connections, it's going to be running two little chains of operations in parallel this time. And it could be that if you've got multiple threads, then a handler for either one could run on any thread at any time. So you say, okay, great, mutex, I'm going to use a mutex. And so you go through and you put a scoped lock into each handler to manage your state. Problem with that is actually, I think I've missed a step here.
Violates the blocking rule.
Yeah, well, it violates the blocking rule, that's right. So, because if it could be that a handler for the same object is currently running on the other thread, and so the mutex is already locked. Your handler is blocked and can't run until the other one finishes. So ideally what you want to do is actually not run the handler straight away, but queue it for later when the lock becomes free. And that's actually what a strand does for you. So a strand says, if it's uncontended, I'm going to run the handler straight away. If it's contended, I'm going to queue it for later. And to use a strand in the connection object here, what you need to do is add an extra layer of wrapping around your function object for your completion handler. So all strand wrap does is create a slightly fatter function object that ensures that the internal function object only executes one at a time for the given strand. So you would, in this particular example, you'd probably have a separate strand object per connection, because you're quite happy for different connections to execute concurrently, but you want to guarantee within that single connection object that it's single-threaded. If you're doing the message passing, it's very similar to what we saw before, except this time you're doing your post or your dispatch through the strand rather than through the I/O service. It just guarantees that that it will not execute more than one at a time within the strand. Okay, but yes, going back to the idea, well, why not still just use a mutex anyway? I'm quite happy to live with the blocking. Well, the problem is actually, if you can see the red, these functions here, these ones, async read sum, are the low-level operations on the I/O object itself, but async write is what I call a composed operation. So it's a higher level abstraction that is implemented in terms of lower level asynchronous operations. And so internally, it actually looks a little bit like this. When you go into this, you perform your chain of async write sums. Now, you've got this problem here. You've got some state which is actually being accessed by these intermediate handlers here, and you need to make sure that those intermediate handlers are also synchronized correctly for your object. Now, a strand does that for you automatically, but what I'm going to show now is how you could actually do that for a mutex to give you an idea of how a strand works. Sorry. So the idea here, yes, you've got a mutex that you want to associate with a given handler. This is just poor man's function call forwarding. And you want to wrap in the similar ways we're calling strand.wrap. We just want to create a new wrapper function object for any function object that we pass in. Now the key part is to use one of ASIO's customization points, which is called an invocation hook. So every single completion handler that runs in ASIO runs through one of these. It's located using argument-dependent lookup, and it allows you to customize how handlers are executed, or how function objects associated with handlers are executed. So what we're actually doing here is saying that for any function f which is associated with our mutex wrapper-based handler, we just want to execute it within a scoped lock. And so this customization point means that every single intermediate handler in that composed operation is executed within the lock. And a strand does a similar thing for you to make sure that every intermediate handler is executed only one, does not execute concurrently. Okay, and yeah, so this is basically the same. Now, I've just got one more section to go. We're running a little bit over time here. So what I want to talk about here is how to manage complexity in your application, because as people have pointed out, as protocols get more and more complex, the chain gets longer and more complicated. So what approaches can you use to manage that? Now, there's two approaches that I recommend, and the first one I'm calling pass the buck, and the second one I'm calling the buck stops here. And the principle of pass the buck can actually be subdivided into functions and classes, and I'm going to give a couple of examples. So if we go back to our proxy connection here, where we've actually got two loops running in parallel, we can actually recognize, but hey, these loops are actually basically doing the same thing. So they're a candidate for some piece of logic that can be abstracted out. So what I'm going to propose is that we're going to write what I call the pass the buck function to do that loop of operation. So I'm going to call it async transfer, and what it does is it takes the two sockets that it's linking, it takes a buffer to use as working space and the handler to call when the overall operation finishes. Now, and yes, so also known as a composed operation, so things that are in ASIO right now, like async write and async read, are equivalent to what we're going to do here. Now, the reason it's pass the buck means pass the buck on ownership, pass the buck on threading, pass the buck on just about everything. This function doesn't want to take responsibility for any of that. Okay, so it's up to the caller to guarantee the lifetime of the socket objects, and up to the caller to guarantee the lifetime of the buffer and so on. So yes, our function is going to be performing this chain of operations, and it's only going to be calling the completion handler if an error occurs. Now, I'll let you read this at your leisure if you've got a copy of the slides, but one way of implementing the function is to do it as two separate completion handler type functions that represent the two functions in this diagram here. So here I simply have a function called doRead that initiates the asynchronous read type. Yep.
I speak only for myself, but I need a break.
We are nearly finished. So.
This is over.
It's going to end right now. As soon as you're done.
Yeah. And the other half, of course, is the do write that initiates the do write operation. At the top, because we want to hide these implementation details from the user of our function, we simply provide the function with the signature that I proposed before, and it initiates the whole chain by calling doRead. Now, another way of implementing it would be to do it as a state machine type approach, whether you're either doing a read or doing a write. And for certain sorts of composed operation, that's probably the right way to go about it. And the way you might implement that state machine is to do it using a function object rather than standalone functions. And so you just store the state as members of your function object, and in the function call operator, you simply do the thing. If I'm doing the read, we initiate the read, otherwise we initiate the write, and it just keeps calling back into this state machine at the completion of each underlying operation. And again, to initiate the operation, we've got the high level, it's got exactly the same signature as the previous implementation, so the user of your abstraction is unaware of how you've implemented it. And then the overall proxy class is simplified to just look like this. After the connection, it simply initiates the 2 async transfer calls to run the bulk of the work. Now, passing the buck on threading means you need to implement one of these customization points, because unlike the previous case where we were customizing it to do a scope lock on a mutex, in this case we're customizing it to pass the buck to the next guy up the chain. And that's what pass the buck is all about, is deferring responsibility on how things are invoked. And this makes sure that your abstraction works correctly with strands. Optionally, you might also use the customization points for allocation, because ASIO will be allocating some objects behind you to do various bookkeeping. So if you want to, you can pass the buck and transfer responsibility for allocating and freeing to the next handler in the chain. If you wanted to, and I'll leave this as an exercise for the reader, or viewer, audience, you could easily implement, you can recognize the fact that that async function doesn't use anything that is specific to sockets. It just works in terms of stream type, ASIO stream type operations. So you can make your functions more generic as you see fit. And the operations in ASIO, like async read and read until and so on, operate at the stream level, not at the socket level. And okay, so another way of doing it would be to recognize that not only do we have the chain of operations, there's also buffers associated with this operation. If you want to hide the existence of the buffers away, rather than writing a pass the buck function, you may choose to write a pass the buck class. The principle is basically the same, except that as data members of the class, adding the additional state that you need to store for the duration of the operation. Now, in this example, there's 2 buffers, one for the upstream side of the proxy and one for the downstream. But what I've done here is I've exposed the 2 operations, upstream and downstream, as public operations of the class. An alternative design, so it looks like that when you implement it. An alternative design would be to do it as a single async run operation. And in this case, the example, the fact that there are multiple chains inside is hidden from the user. In both cases, it's the responsibility of the caller to maintain lifetime of the object. There's no lifetime management, no enable shared from this. In fact, this class works equally well if you use enable shared from this, or you store it on the stack, or whatever you choose to do. And again, if we implement our proxy, it looks like that. Now, so in that case, the operation inside that pass the buck class sort of looks a bit like this. So it sort of forks off, and then you've got 2 chains of operation that run on indefinitely, whereas the original case is more like there's 2 chains of operation that run side by side, and actually the caller is entirely aware of them. Now, I would actually argue, in terms of pass the buck being the principle, that this is the approach you should use, because you're passing the buck on the chains themselves further up the application. Okay, so the other approach is the buck stops here, and actually it looks fairly familiar because it uses enable shared from this. It uses shared pointers. In this case, you're really implementing, so let's skip through, the equivalent of the top level class. And it's, I would say in a fairly large application, you will end up having multiple buck stops here abstractions communicating with each other in much the same way as if you're just writing the top level of the application. So you can also provide reusable components using the same approach that you would use in just writing the application itself. I'm sort of glossing over a few things here because we're short on time. But yeah, so the principle in any application, the buck's got to stop somewhere, right? So you should consider structuring your application in terms of passing the buck, and some of that buck passing will occur in ASIO, and some of that buck passing may occur in your own abstractions, but ultimately, at the top level, you've got something like the enable shared from this approach, which is taking responsibility for threading and memory allocation and whatever else. Now, the great thing about when you put these two things together is that you don't have to use enable shared from this. I'm not saying you have to. If you can manage your object lifetimes at the top level of your application, it doesn't necessarily mean on the stack, it could just mean putting them into an SDL container or whatever, then you don't need to use shared from this, you don't need to use anything like that, and so you're no longer paying the cost of reference counting. If you also customize the memory allocation, you can make use of the fact that you know how many chains there are going to be in your application up front to commit all of the memory that you need up front and recycle that memory. So you can end up using these two facts to put together an application that has no reference counting costs, all the memory is committed up front, and you have zero allocations in the steady state of your application, which can be important if you're doing low latency or embedded or whatever. So yes, just to summarize, the four main challenges that we had, I proposed 4 guidelines. One is to know the object lifetime rules. So even if you choose not to use the shared pointer approach, pay attention to ownership and how ASIO will copy objects for you to use that to your advantage. Secondly, in terms of thinking asynchronously, assume that most things will change under your feet, but at the same time you need to maintain, keep track of the state that you know is under your control, because that's the key to writing a working application. Thirdly, as a general rule, prefer to keep your application single-threaded, and even if you really do need to use threads, try and do it in a way that the majority of your logic will still be single-threaded, because you don't have to deal with issues to do with synchronization. And finally, as a principle, if you want to manage complexity by writing abstractions of your own, try and employ the pass the buck principle as much as you can. So yes, make it somebody else's problem. Okay, that's it. Thank you.